Now that we have a good understanding of the division algorithm, I'm going to show you a common way that the division algorithm can be used in proofs about integers. So we're going to look at using the division algorithm in congruence proofs. First, we're going to review what proof by cases, how that works, and what the division algorithm is. And then we're going to show how these techniques can be used in a congruence proof. Alright, so here's how the proof by cases process works, just to give you a reminder back from section 3.4. So our theorem is going to be, we're going to be assume some assumptions, we're going to show some kind of conclusion. And what we're going to do is break down our assumptions into cases. The cases should combined cover all the possible ways that assumptions can be true. And for each individual case, you not only assume the assumptions from your theorem, but you also assume whatever assumptions that go with that case. And then you prove the conclusion for every single case. And remember, that means you have a separate proof for each case. And here is the statement of the division algorithm that we just got finished looking at. If a and n are integers where n is a positive number, then there exist unique integers q and r, that's the quotient and the remainder, such that a is equal to nq plus r, and 0 is less than or equal to r, and is less than or equal to n minus 1. So our remainders are all non-negative and no bigger than n minus 1. And as a consequence of that, you can see from the equation a equals nq plus r that a is congruent to r mod n. Then it immediately follows that if a and n are integers with n positive, then a is congruent to r mod n for some integer r, where r is between 0 and n minus 1. Alright, so let's see the theorem or the problem that we're going to work on that's going to eventually be the theorem that we're going to prove. So suppose m is some random integer, and it can literally be any integer. When I square m, what is it going to be congruent to mod 3, or what are the possibilities? Well, the possibilities for any integer is going to be 0, 1, or 2, but we don't know. It could be, we don't know which of those it's going to be for m squared. So let's check out some integers and see what we get. So 1 squared is equal to 1. So that's congruent to 1 mod 3. For 2 squared we get 4. That is congruent to 1 mod 3 as well. We see a pattern building. 3 squared is a little bit different. We get 9, which is congruent to 0 mod 3. But then when we get back to 4, we get 16, which is again congruent to 1. We get the same pattern going over again. 5 squared is 25, which is 1 mod 3. And then 6 squared is 36, which is 0 mod 3. So we can sort of see a pattern emerging here. It appears that sometimes m squared could be congruent to 0 mod 3 or 1 mod 3, depending on the value of m. But not 2. So that's basically the theorem says that we can never get m squared congruent to 2 mod 3. So do we see any patterns? Well, if you look at m squared, right, we get 1, 1, 0, 1, 1, 0, 1, 1, 0, mod 3. And so it appears that the pattern repeats every 3 numbers, which suggests that we might want to look at the division algorithm with n equal 3, right? So we're going to divide by 3 and look at the possible remainders. That can tell us something about patterns that repeat every 3 integers. Alright, so our division algorithm, now we're going to divide by 3, right? So our division algorithm there says our equation is going to be m equals 3q plus r. We're dividing by 3, we get a quotient of q and a remainder of r. And since we're dividing by 3, our remainders are going to be either 0, 1, or 2. So that's what the division algorithm is going to say, right? It's going to be at least 0 and at most 3 minus 1. So that gives us 3 possible cases, right? If we have a random integer, either our r is equal to 0, or it's equal to 1, or it's equal to 2. So those are the only 3 cases that we can have by the division algorithm. And therefore, those are the only possible cases that we have to consider. So if we look at r equals 0, m is equal to 3q plus 0, which is just 3q. And if we square that, we get 9q squared. We can factor a 3 out of that to get 3 times 3q squared, which means that m squared is going to be congruent to 0 mod 3, which is kind of what we expected, right? If anytime we had a multiple of 3, we always got 0 mod 3 when we squared it. If we have r equal 1, well, then our m is going to be 3q plus 1. we square that and multiply everything out. We can then factor out a 3 from those first two terms, and what we end up with is m squared is congruent to 1 mod 3. And then when we do r equals 2, we get m is equal to 3q plus 2. We square that out. We get 9q squared plus 12q plus 4. We have to do a little finagling with the 4, split it into 3 plus 1, but then we can factor a 3 out of those first three terms, and then what we end up with is that m squared is congruent to 1 mod 3. So if we look at the three possibilities, one of those possibilities gives us 0 mod 3, the other two gives us 1 mod 3, which proves our theorem. So now we're ready for the formal proof. Let m be an integer, then m squared is either congruent to 0 mod 3 or 1 mod 3. Alright, so we are going to state what our assumptions are and what we're going to prove, and then we're going to warn our reader that we're going to be using proof by cases. So we assume m is an integer, and we're going to show that m squared is congruent to 0 mod 3 or m squared is congruent to 1 mod 3. So the division algorithm tells us that we have m is equal to 3q plus r, where q and r are integers, and r is between 0 and 2. Again, we're just stating exactly what the division algorithm says when n equals 3. That means we can have r equals 0, r equals 1, or r equals 2. We're going to prove the theorem separately for each case. So we're telling our reader actually two things. First of all, that we're doing proof by cases. And secondly, that the three cases we're going to consider are r equals 0, r equals 1, or r equals 2. And everything else is going to work just like the computations we did in the previous slide. So in the case r equals 0, we have m equals 3q. And so we look for m squared, do the exact same computations as before. Now here we have to do a little bit justification on that 3q squared. Since the integers are closed under multiplication, we have 3q squared is an integer, and so m squared is congruent to 0 mod 3. Yay! One case down, 2 to go. For the case r equals 1, we have m equals 3q plus 1, and then we do the exact same computations that we did before. Now we have to do a little justification step. We have to use the fact that the integers are closed under multiplication and addition, and therefore 3q squared plus 2q is an integer, and that will imply that m squared is congruent to 1 mod 3. And then finally, for the case r equals 2, we have m is equal to 3q plus 2. We do the exact same computations as we did before for m squared. We have to justify that 3q squared plus 4q plus 1 is an integer. We do that using closure of the integers under multiplication and addition, and so m squared is congruent to 1 mod 3. So we've gotten to the last case. We just have to warn our reader, hey, we proved that in all cases we have m squared is congruent to 0 mod 3 or m squared is congruent to 1 mod 3, and so the theorem is proven. Alright, so now after seeing that one, I think you're ready to work on the activities. The name of the PDF file that's included with this video is Division Algorithm Proofs, and you can go ahead and work on those.